Let's talk about ammonia. Ammonia is NH3, and it was one of the substances that we tested yesterday in the Google Hangout. Um, I tested it, and maybe I should have made a bigger deal about this at that time. But ammonia is a base. It was not as strong as a base as sodium hydroxide, but when I added different indicators to it, like for instance, when I added bromethymol blue to it, it definitely turned it blue for sure. So that means it's a base. So here's the question I have for you. Let's write the dissociation reaction and explain why it's a base. So I go da da da, and then I'm going to go. Wait a minute. Wait a minute. How is that a base? Based on our explanation of these guys up here, these are Arrhenius bases. How is NH3 a base when an Arrhenius base says it has to contain OH? Here's the downfall of Arrhenius acids and bases. It was the original definition of acids and bases, and they found that there are more substances out there that meet the requirement or that have the physical properties of acids and bases. And so they limited that to basically they had to expand it. And the Bronsted, there was a guy by the name of, or two guys actually, who were named Bronsted. Let me scroll down. Lowry, acids slash bases. And they came up with their own method for determining acids and bases, and it helps explain what ammonia is. And the way that they do that is instead of just showing it dissociating, they show it reacting with the water. And this is actually in equilibrium, capital O. So I'll go like that. And so we have ammonia reacting with water, and the products of this is going to be NH4 positive plus OH with a negative. So wait a minute. Let's think about what's happening in this reaction here. So now let's talk about what's actually happening. So when I have the particle diagram here, I know the shapes look kind of weird, but remember the reason I did it like this way is to reflect the actual geometry of the molecule. Ammonia is that trigonal pyramidal. And so its bond angles are slightly less than 109.5, and water is bent, if you remember. But basically, what this reaction is saying, if what this is saying is true here, ammonia right there is reacting with water right there to form ammonium, then what's in the hydroxide? Then what we're doing is basically taking one of these hydrogens from here and moving it here to form the ammonium molecule. And this is in equilibrium, which means that it's bouncing back and forth depending upon what the equilibrium constant is. So that is your product there of NH4 and ammonia. So the question is, what is a Bronsted-Lowry base? Well, a Bronsted-Lowry base, I'll go BL base is, all it does is describe what the ammonia did here. What did the ammonia do to a hydrogen? Well, it accepted a hydrogen. So its definition doesn't have anything to do with properties or anything like that. The Bronsted-Lowry base is defined as a hydrogen ion donor or acceptor. It accepts hydrogen. So that would imply that maybe something like hydrochloric acid, on the other hand, is the opposite. So let's just look at hydrochloric acid and let's see if we can define it in terms of Bronsted-Lowry terms. So let's just say we're reacting that with water here to form. And so what would we form in this case? Well, if the Bronsted-Lowry base is a hydrogen ion acceptor, then I bet that an acid is a hydrogen ion donor, and in fact it is. I'll go ahead and write that down here. So a Bl acid is a hydrogen ion donor. And so when it donates a hydrogen, we know hydrochloric acid is an acid, so it's probably going to meet this. It's going to donate a hydrogen. Well, where's it going to donate it to? To the water. Ooh, that sounds interesting. So basically we're going to form what, like the chloride ion, but then we're also going to form the hydronium ion. It's because we have to add an H to H2O, and this is called hydronium ion. And this is very characteristic of Bronsted-Lowry acids, is oftentimes they will form, or most times, they will form what's called the hydronium ion. And this is actually a better representation of what's actually happening in the solution of water, because the water molecule does actually interact with the hydrochloric acid to help form that positive ion that we're seeing that's causing the conductivity. So to summarize, the Bronsted-Lowry acid is a hydrogen donor. The Bronsted-Lowry base is a hydrogen acceptor. And we also, this leads to huge implications on this kind of reaction right here. Like, for instance, we know that ammonia is the Bl base because it is accepting a hydrogen from the water. Wait a minute. The water is giving a hydrogen to the ammonia? Well, if it's donating a hydrogen, that means that in this case, water is a Bronsted-Lowry acid. What? Water is an acid? That seems crazy. Well, let's look down here on this example here. We know that hydrochloric acid is a Bronsted-Lowry acid because it donates a hydrogen to the water. Wait, it donates it to the water, so the water accepts a hydrogen? Oh, so that means that water, in this case, according to Bronsted-Lowry, is a Bronsted-Lowry base. Here's the deal about water. It is what's called amphoteric. It can be both an acid and a base in terms of Bronsted-Lowry definitions. And so we have both reactants acting as an acid or a base, depending on what you need it to do. And so one last thing about this is, because these reactions are reversible, it's also good to identify the acid and bases on the other side in terms of Bronsted-Lowry definition as well. So if I'm going from ammonium here to, and ammonium and hydroxide to water and ammonia, then the ammonium is going to have to give its hydrogen to the water, or to the hydroxide, to make water. So that means that the hydroxide is accepting hydrogen. Because it's accepting, we know that's an acid, because acids accept, or excuse me, bases accept. And so hydroxide is the base on the product side, and they call that the conjugate base. Now, the ammonium is donating its hydrogen, and because it's on the product side, it is going to be called the conjugate acid. Therefore, basically, on both sides of this reaction, we have proton donors and proton acceptors. So the same thing down here, so we'll identify those real quick. The H3O with a positive charge, it is going to have to donate a hydrogen to the chloride ion, making it the conjugate acid. And the chloride ion, you guessed it, is accepting a hydrogen, making it the conjugate base. So in these reactions that we can write now, we should be able to identify Bronsted-Lowry acids and bases on both sides. The reason, the difference between a conjugate acid and just a regular Bronsted-Lowry acid is the side of the reaction it's on. They're both acids, and they're both bases in that case. But we need to be able to identify acids and bases on both sides. And to help us in terms of terminology, they use the word conjugate to help identify, oh, it's on the right side of the reaction. And that's all.